Okay, so in this video I'm going to be recording solutions for the 2022 Exam 2 VCAA paper. Exam 2 multiple choice, 20 multiple choice questions, 60 marks worth of short answer, extended answer questions, and in 2022 there was 5 extended answer questions. Obviously, 2023, we're in a new study design. The vast majority of the content in these old exams is still relevant. The only major thing that is removed is matrices, although most of the matrices questions are transformations questions, and they can be rewritten to still be accessible this year. The transformations content is still worth doing. They'll find different ways to ask that. So I think it's still worth doing those questions. So I don't think there'll be many things we'll skip over here. Obviously, missing from this paper will be all the new content, pseudocode, Newton's method, trapezium method. Yeah, things along those lines won't be assessed in this exam. I've got my CAS sitting here ready to go, which we can use freely throughout the exam. And I've also got the formula sheet available to me over here, although of course you've also got your bound reference to access any formulas you might need. Okay, let's get started with the multiple choice. So it's become pretty standard for question 1 to ask you about period and or amplitude and or range of a trig function. The period of this function is, so the plus pi is not relevant, that's a horizontal translation. The 2 is what's relevant here, that's a dilation by a factor of a half from the y-axis. And so that means that the period goes from being 2 pi, which is the period for a standard cos graph, to having been dilated by half from the y-axis. So dividing by 2 or multiplying by a half, and so we have a period of pi. So B is the correct answer to question 1. The graph of y equals 1 on x plus 3 all squared plus 4 has a horizontal asymptote with equation. So this is a truncus. It's gone to the left by 3 and up by 4. So left 3, up 4 will mean that the horizontal asymptote will be at y equals 4. And it'll be a truncus. So y equals 4, option A. Question 3, if in doubt, you could get your CAS to draw it. The CAS doesn't draw in the asymptotes though, so you would sort of be speculating as to what you think that asymptote would be. Better to have an understanding about how the functions actually work. The gradient of the graph y equals e to the 3x at the point where the graph crosses the vertical axis is equal to. Okay, so we could definitely use our CADs to help us here. The algebra of this is pretty straightforward. I could probably do this quicker by hand. But if you wanted to define your function with your CAS using the proper e to the power of 3x, we want to obviously know where that graph crosses the vertical axis. So that is f at 0, which is clearly going to be 1. So again, as I said, I could have done that quicker in my head. So in terms of where it crosses the vertical axis, that's going to be at the point 0, 1. So we want to know the gradient, that is the derivative, dy dx at this point. So again, dy dx, again I can do this quicker by hand, derivative of e to the 3x. I've got my formula sheet available to me if I need. Oh, sorry, just dropped the pen. So derivative of e to the ax is ae to the ax. So over here with my CAS, that's going to be 3e to the 3x. And I want to know the derivative when x is equal to 0, which is the vertical axis intercept. So actually I didn't even need the coordinates, did I? I just needed when x is 0. And so therefore dy dx will be 3e to the 0, which is 3 times 1, which is 3. So as I said, we could have used our CAS. We could have got our CAS to differentiate f of x for us, and then obviously work out the derivative given that x equals 0. Which would be 3. Question 4. Which of the following functions is not continuous over the interval 0 to 5? Okay, so we could use our CAS to help us sketch these graphs, but we really just need to be able to think them through. I actually think A is going to be the option here. Oh no, sorry, it's gone the wrong way. So that's a truncus gone to the left by 3, so 0 to 5, we would definitely be continuous for that function. Remember, continuous, we can draw the graph without lifting our pen. Essentially, the square root graph that's a square root graph translated to the left by 3 again. So left 3, square root, no other things happening. So over 0 to 5, that is definitely continuous. So 0 to 5 being, you know, this region here. Definitely continuous over that region. Part B is a cubic, not a cubic, sorry, it's an inverse of a cubic, so it's a sideways cubic, x to the power of a third, looks like this, again, over that shaded region, yellow region from 0 to 5, that is definitely a continuous function. Part D, tan. Okay, so we're going to need to think about where these asymptotes are, so our CAS might have actually been useful here. We probably need our CAS for these last two, so we've definitely ruled out that it's not these three options. We can draw tan of x on 3, obviously, so the period of tan is pi divided by a third, so the period of this is going to be 3 pi, and 3 pi is, let's just get ourselves a decimal, 3 pi is 9.42. Half of that, which is where the asymptote will be, is at 4.71. So the asymptote is going to be at x equals 4.71 for that tan graph. And so therefore, it's definitely not continuous over this interval, so I suspect it's going to be that one. Sine squared x on 3, let's have a quick look at what that looks like on our CAS. So to put a sine squared into our CAS, we need to actually understand what that means. It's terrible notation. It actually means sine of x on 3 all squared, and our CAS will only understand it that way. And that certainly appears to be continuous over 0 to 5. So it's the tan function, and it's because that asymptote does fall within the domain from 0 to 5. So D. Question 5. The largest value of a such that the function, so it's a quadratic over a restricted domain, where f is 1 to 1 is. Okay, so we need f to be a 1 to 1 function. We need the largest value of a. I've got my CAS happening here. Delete, delete, delete to get rid of that. Let's just sketch this. Oh, sorry, didn't mean that. Let's just sketch this quadratic. X squared plus 3x minus 10. Okay, so we want to go from negative infinity to a. Let me just adjust that a little. More than that. I'm going to struggle to click on that number now. It's a bit fiddly if it hits right near the graph. Let me just adjust that minimum y value. Okay, so I'm interested in where that turning point is. Given that it's a, okay, so negative 1.5. So the largest value of a such that f is 1 to 1 is. Okay, so obviously as long as a is anything less than 1.5, it would definitely be 1 to 1. The biggest value of a is negative 1.5, and so that is option C. But it may have been that negative 1.5 wasn't an option. If that was, say, positive 1.5, that wouldn't have worked, and that would have meant B is the correct answer to this question. It's the largest value of A of the options here, such that it's a 1-to-1 function. So, but in this case, that actual value is there. So if we let A be negative 1.5, then the domain will be restricted to be just negative infinity to negative 1.5, and so we'll just have that complete half of the parabola to negative 1.5. And that is a 1-to-1 function. Which of the pairs of functions below are not inverse functions? Okay, so I could probably just think through the rules, but I suspect that domains are going to come into play. So this is definitely the inverse of this. If you think about swapping x and y in that original function and rearranging, swapping x and y and rearranging to make y the subject, you'll get x minus 3 equals 5y, and so y equals x minus 3 on 5. So the rules are definitely inverses. The domain and range of the linear function is R, and so therefore the domain, the range of the f is R, and so therefore that becomes the domain of G. So A is definitely correct. They are inverse functions. If we have a think about B, again, swapping x and y, so x equals 2/3 y plus 2, so taking away 2, and dividing by 2/3, which is multiplying by 3 on 2. So it's going to be 3 on 2x minus 3. So the rules definitely work. Again, the range of the original linear function will be r, and so therefore the domain of the inverse function will also be r. So B is correct. They are inverse functions. Option C, the rules are definitely inverses. We just need to check the domains. So x squared, but where x is less than 0, so that would be the original domain. And then square root of x, actually the rules are not inverses because we've got the positive square root of x and they are not inverse functions. So it's going to be this one here. This would have needed to be the negative square root for these to be inverses. So remember, we're looking for a mirror image in the line y equals x. So option C looks like it's going to be correct. We can check through the others while we're here just to be confident that we're right. So the inverse of 1 on x is 1 on x, correct? If you have that and you swap x and y, you get x equals 1 on y, and rearranging that you get xy equals 1, and so y equals 1 on x. So 1 on x is definitely the inverse of 1 on x. The range of 1 on x will be x excluding r excluding 0, so that's correct. That's the domain and the range, and so therefore the inverse makes sense. So D, they are definitely inverses of each other. And then f of x equals log e of x plus 1. So again, if we swap x and y there, so we get log e of y plus 1. We take away 1. And e to the power of x minus 1 will be y. So the rules are definitely right. The log function is a log shifted up by 1. So its range of f will be r, and so therefore that becomes the domain of the inverse, and so that's correct. So they are certainly inverses. So C is the one. It needed to be a negative square root of x given this domain being the left-hand side of the parabola. Okay, oh, sorry. Let's circle that. So C for question 6. Question 7. The graph of y equals f of x is shown below. The graph of f dash of x, the first derivative of f, could be. Okay, so it looks like f might be a cubic. It's a slightly strange shape, but it doesn't really matter. Its inverse is possibly going to be a parabola, but it might not be. In fact, none of these are parabolas, so I suspect the original is not actually a cubic. But the key things are to look for things we know about the derivative. So we know that when at this turning point here, the derivative will be 0, so therefore the derivative function will go through the x-axis at that point. Similarly for this turning point here. So the derivative function is going to have 2 x-intercepts, and they're going to be at those 2 locations. So on that basis, I can rule out A, and I can rule out C, and I can rule out D. So it's either E or B. Okay, and so that's a fairly easy distinction, just in terms of the gradient before that first x-intercept is clearly positive, so the graph's going to be up here, it's going to go through this point. The gradient between those 2 turning points is negative, so it's below the x-axis here, and it's after there. So in terms of the shape, I don't really know what it looks like, but it's essentially going to be above the x-axis, it's going to go through there, it's going to go through there, and then be above the x-axis again. So it needs to be this E shape, not the B shape. Question 8. If the integral of f of x from 0 to b is 10 and the integral of f of x from 0 to a is negative 4, where 0 is less than a, which is less than b, then the integral from a to b of f of x is. Okay, so essentially what we've got here is, let's just think about what's happening. So we've got 0, then a, and then b. Okay, we know that the integral of f of x from 0 to b is positive 10, but from 0 to a is negative 4. So let's say our graph of f is probably going to do something like this. It's not very good. Let me make a closer. It doesn't really matter how accurate my graph is, but let's say something like that. Okay. So what we're saying is the integral from 0 to 10, so this bit here, sorry, the integral from 0 to a is negative 4. So therefore that area there is going to be 4. Okay. The integral from 0 to b, sorry, is positive 10, but that factors in this negative 4 little bit. So that means this bit here must actually be positive 14 in terms of area. So that this integral under the x-axis is negative. Its area is 4, but the integral will be negative 4. Therefore, when I integrate from 0 all the way up to b, I'm going to have a negative 4 plus some unknown value, which is that, has to give me 10. And so therefore that unknown value has to be 14. So that's how I've worked out that this must be 14. And that's the integral that I'm being asked to calculate. The integral from a to b is indeed 14. We probably could have done that just more algebraically rather than thinking graphically, but I find it quite helpful to think graphically about what's happening. So we could have thought about the fact that the integral from 0 to b of f of x is the integral from 0 to a of f of x plus the integral from a to b of f of x. Okay, we know that this integral from 0 to b is 10. We know that this integral from 0 to a is negative 4. And this is the thing that we're trying to find. And so we add 4, and so therefore that is 14. But it certainly follows from the graphical application we looked at earlier. Okay, question 9. Let f be a function with the domain 0 to infinity, inclusive of 0, and it is a square root function. The shortest distance d from the origin to the point xy on the graph of f is given by. Okay, I actually recall from last year I didn't like this question. I didn't actually agree with the wording originally. It is technically correct, but I don't really love it. Let me get my head back around it. I haven't done this paper for nearly a year. The shortest distance d from the origin to the point xy. Okay, so this point xy, x and the y value is going to be square root of 2x plus 1. So that means if I think about drawing a triangle here, this distance here is x and this distance here is 2x plus 1. And so therefore I can get an expression for d. D squared is going to be x squared plus square root of 2x plus 1 squared. And so therefore it is x squared plus 2x plus 1. And therefore d will be the square root, only the positive square root because it's a distance. It will be that value. Okay, so that expression there that we've just found, that is the expression for the distance for any value of x. So now we actually want the shortest distance. And so therefore if we think about differentiating that, so let me go over here to my CAS and do a derivative of the square root of x squared plus 2x plus 1. I've actually never seen my CAS give me that sine function. Alright, let's actually think about that ourselves. So this is x squared plus 2x plus 1 to the power of a half. So therefore the derivative of that is half times all of that to the negative a half, and then times 2x plus 2. And so that is 2x plus 2 over 2 root x squared plus 2x plus 1. So we've got a nice common factor of 2 there. So it's going to be x plus 1 over square root of that. Okay, I've remembered what the issue is here. So by differentiating, sorry, I just had to pause and think about this again. By differentiating it, I'm actually trying to find the value of x that gives the shortest distance, whereas that's actually not what the question asks for. The question is just asking me for the distance from the origin to any point xy, which is actually what I've found up here. By the shortest needs to be there because it's the direct distance, the straight line distance. So the derivative is actually not relevant here. Now the challenge here was that I and probably many students got led to thinking, okay, I'm going to need to differentiate this and solve that derivative equal to 0. Because that wasn't an option. Okay, so the answer I've got here isn't any of the things. This one looks similar, but there's a minus here when there should be a plus. These ones here are tempting if you, but they should be d squareds. Well, not quite. That should be a square root in there. Oh no, that one's right. The second one's not quite right. So they're sort of versions of what you get along the way. D is not quite the answer that you get. But actually, sorry, C, I should say, is not quite the answer you get. Actually, if we have a look at this, x squared plus 2x plus 1 is x plus 1 all squared. And so the square root of x plus 1 all squared, the positive square root of x plus 1 all squared, is just x plus 1. And so the distance from the origin to the point x, y will always be x plus 1. And that will be the shortest, meaning the most direct distance. You're not being asked to minimize that distance. You're being asked to give a general expression for the distance from the origin to any point on the graph, but it should be the straight line distance, and that is option D, x plus 1. But yeah, I thought this was sort of a bit of a mean question. The shortest seemed to imply that we should be minimizing. I understand that it needs to be there, but I think the phrasing of it made it confusing. Question 10. An organisation randomly surveyed 1,000 Australian adults and found that 55% of those surveyed were happy with their level of physical activity. An approximate 95% confidence interval. Okay, so this is a straight CAS question. We're going to go to menu 6 for statistics, 6 for confidence intervals, and 5. We're going to need the number of successes, so 55% of those surveyed, so we need to know what 55% of 1,000 is, and so that's going to be 550 successes out of 1,000 people, and we want a 95% confidence interval, so we'll leave that confidence level at 0.95, and our confidence interval is this C lower and C upper values that we're seeing on the CAS there, and so correct to 1 decimal place seems to be all my options. For the percentage, good. So for the percentage of. So the confidence interval is 0.5192, 0.5808, but it does say the percentage. So 0.5192 is equivalent to 51.9% to 58.1%. So we should have that 51.9 to 58.1, so option D, question 10. Okay, question 11. If the derivative of that is that, then the antiderivative of that is that. Okay, so we need to reverse the information we've got about the derivative. So if we know that the derivative of the yellow thing is the green thing, then the antiderivative of the green thing is the yellow thing. So the information being given tells us that the antiderivative of sine of x plus x cos of x is x sine of x. We want to know what the antiderivative of x cos of x is equal to, so we're interested in this part of our antiderivative. So we can split this antiderivative up and subtract the sine of x bit. So this is the antiderivative of sine of x with respect to x plus the antiderivative of x cos of x with respect to x equals x sine of x. And obviously there's a plus c going on here, but we can just stick that on at the end if we want. We can see that all the options have a plus c on them, so you can not worry about that too much. Let's subtract the antiderivative of sine of x, and you can see that all these answers still have that antiderivative sitting in it, so I'm not going to evaluate them. And they've left that there because this is a way of forcing you to have to do this by hand and not just plug this into your CAS. It won't actually give you any of the options available here. So antiderivative of x cos of x dx is x sine of x, and again I'm just going to stick the plus c's on at the end. It gets in the way if you're not careful. Take away the antiderivative of sine of x. Okay, now then if I need this 1 on k out the front here, I'm going to stick a 1 on k out on this left hand side, then I also need to stick a 1 on k on the right hand side, and so I'm going to have 1 on k times, actually let me just see if that matched any of my options right there. I think it probably did. I think that was option C. And then, as I said, there should be a plus C here all the time. We can just stick it on the very end. So I think this option matches this one. 1 on k, brackets, x sine of x minus integral and plus C. So option C. Okay, question 12. The bag contains 3 red pens and X black pens. 2 pens are randomly drawn from the bag without replacement. The probability of drawing a pen of each colour is equal to. Okay, so we've got 3 red pens and X black pens. So I just think through a tree diagram here. So we've got red and black. So initially we have X plus 3 pens in total. 3 of them are red, so the probability of getting a red is 3 over X plus 3, and the probability of getting a black is X over X plus 3. Okay, we're drawing 2 pens, and we're drawing them without replacement. So we don't put it back, which means the denominator here is going to be X plus 3 take away 1, so that's going to be X plus 2. So we now only have X plus 2 pens in the bag. If we do a red first, we only have 2 reds left, but we still have X blues or blacks left. If we drew a black first, we still have 3 reds, but we now have X minus 1 blacks. Okay, so we want the probability of drawing a pen of each colour. So red and then black, or black and then red. So this probability is going to be, is going to be 3 on X plus 3 times X on X plus 2. Everything is going on around me right now, so I'm sorry if you can hear that. There's a very loud dog barking and my washing machine spinning. So X plus 3, you must think I wash all the time. It just seems to happen that when I'm home I'm trying to record videos and do some domestic things at once. Okay, so that's this probability, and then this one here will be X on X plus 3 times 3 on X plus 2, so it's actually going to give us the same thing, 3X on X plus 3 times X plus 2. And so therefore we're going to add those two probabilities together, which means we're going to have 6X on X plus 3 times X plus 2, which is option A. Alright, and then question 13. The function f of x equals log e of x plus a on x minus a, where a is positive, has the maximal domain. Okay, so we need the range of this thing, the range of this fraction, to be a subset of the positive real numbers for the log to exist. Okay, so we need the range of x plus a over x minus a to be a subset of positive real numbers for all of this to happen. So we need to think about that. So I need to think about this function x plus a, x minus a. I'm actually going to, that's going to be a hyperbola, but it's not in a very nice format. But I can get my CADs to help me with this by using just the fraction tools, either from the algebra or the number menu. So I've used algebra. Fraction tools is option 9. I want to write it as a proper fraction. And so if I put this fraction in here, it might give me some domain problems with the a, but let's see what happens. Okay, so that's going to rewrite that in that form. So we know that this is the same as 2a on x minus a plus 1. So if I were to sketch that graph, that's a hyperbola that's gone to the right by a and up by 1. So I'm going to have y equals 1, and I'm going to have x equals a, and it's a hyperbola. So it's doing this sort of thing. So we need the range of this hyperbola to be positive real numbers only, or a subset of the positive real numbers only, which means that we don't want this bit. Okay, we also don't want that bit. So we need to actually work out what that number there is. So that's probably easier to do from the original format. So x plus a over x minus a equals 0, which means that x, oops, sorry, I've actually drawn my graph in a slightly misleading way. X plus a equals 0, and so x is negative a. So let me just redraw my hyperbola. I've got that on the wrong side of the axis. So actually, my hyperbola is crossing here, where that's negative a. Okay, so for it to have a domain that is a range, sorry, that's a subset of the positive real numbers, I don't want to include that negative a. So I'm going to need x is less than negative a, union x is bigger than positive a. So if I've got that bit of the hyperbola, then the range of that is only positive real numbers, and then those will be able to go into the log, because the log has an implicit domain restriction. And so we need to write that in a format that matches our answers. So this is x is an element of negative infinity up to negative a, not including that, union a to infinity, or that's not matching it either. We're going to say it's all the real numbers except for, and we do want to exclude negative a, and we do want to exclude positive a, so they should be square brackets. So option C. Question 14, a continuous random variable x has a probability density function given by this. The expected value of x corrected 3 decimal places is. Okay, so we should be able to just use our CAS here. So expected value of x is the integral over the domain, which is going to be 0 to infinity. Now that's not a mathematically correct thing to write, but my CAS will evaluate it that way. And I need x times my function, and that's going to give me my expected value of x. So let's work that out. Shift plus 0 to infinity, so we get that from the pi button down here. And we're going to need x times our function, which is 2/9 times x times proper e, not letter e, to the 1/9 x squared. Alright, and that is about 2.6587. So 2.659, option B. Okay, maximal domain of the function with this rule. Okay, so again, this is quite like this question up here, question 13. In fact, it's probably a bit easier because we could just draw our CAS to have a look at it. That would be the quickest way probably if we're not sure about the algebra here. So if I just drew the square root of, sorry, something there. Let's try that again. Square root of x squared minus 2x minus 3. And so we can see pretty clearly that there looks like there's x-intercepts at -1 and +3. We could probably get our CAS to check that. F1 at -1 is 0 and F1 at +3 is also 0. So yes, there are x-intercepts there. And we can see that the maximal domain is from -infinity up to -1, including -1, and then from +3 up to infinity. So we can see that it's E just from a simple graph sketch. But again, it's also about the composite function thing. We would need the range of that to be from 0 to infinity, inclusive of 0. And so it's about thinking about sketching that parabola, but much simpler to just draw the graph directly in this question. So actually I think question 15 is an easier question than question 13 and should really be earlier in the paper. Question 16. So we've got a cubic function with some unknown coefficients. M, N, and P are all real numbers, so could be positive or negative, could be fractions or decimals. The cubic function has turning points at x equals -3 and x equals 1 and passes through the point 34. Again, I think this is a pretty routine question, really. So I'm going to define that general function in my CAS. So f of x is going to be 1/3 x cubed plus m times x squared. Be careful about those explicit multiplications. Plus n times x and plus p. Alright, we know we have turning points at x equals -3 and x equals 1, so that means that we know that f dash at -3 is 0, we know that f dash at 1 is 0, and it passes through the point 3, so point 34, so f of 3 equals 4. So those are our three simultaneous equations we'll use to solve for m, n, and p. In entering simultaneous equations involving derivative in the TI Inspire CAS, it's really fiddly in the simultaneous equations. So it's going to be best if I define another function which is my derivative. So menu 1,1, I'm going to define df as the derivative of f. I'm literally just going to, not antiderivative. I'm literally just going to define that as the derivative of f of x. And that's just going to make it much easier for me to put those substitutions into the derivative. So now I'm going to solve simultaneous equations. I have three equations. My unknowns in those equations are m, n, and p. And those equations are that the derivative of f at -3 is 0. that the derivative of f at 1 is 0 and that f at 3 is 4. And there we get m is 1, n is negative 3, and p is negative 5. So option B. Okay, question 17. A function g is continuous on the domain a to b and has the following properties. The average rate of change of g between a and b is positive, so that means the average gradient is positive, which means b will be, the y-coordinate at b will be bigger than the y-coordinate at a, it'll go up on average. The instantaneous rate of change of g at x equals a plus b on 2, so that's halfway between a and b, is negative, so the gradient at that point is negative. Therefore, on the interval a to b, the function must be. Okay, so what we have happening here, as I just said, is a to b. If the average rate of change is positive, then the y value here must be lower down than the y value here. Okay, that must be happening. But then we also know that at a plus b on 2, which is halfway, the gradient is negative. The instantaneous rate of change is negative, so the graph must be going down at this point. So we have to have something that maybe does, something like this. So that the average rate of change is positive, but at this moment the rate of change is negative. So therefore, on the interval a to b, the function must be many to 1, 1 to many, 1 to 1, strictly decreasing, strictly increasing. Okay, so we can definitely rule out strictly, it's definitely not decreasing, it's increasing on average over that domain, but it's also not strictly increasing because the gradient isn't always positive over that interval. It's definitely not going to be a 1-to-1 function, it has to bend back, so it's definitely not going to be that. And then it's about whether it's 1 to many or many to 1, and so this is about us understanding what those things are. So many to 1 means that we have many x values, we have many x values with the same one y value. So for example, if I think about here's one y value, and there are many x values, meaning more than one, that have that same one y value. So this is definitely a many to 1 function. 1 to many actually wouldn't be a function. 1 to many would mean, it would have to bend this way. One x value has many y values. And so actually by definition it wouldn't be a function at all, and we know that it's definitely a function. So this one has to be many to 1, option A. Okay, question 18, so we're into the last 3 of the multiple choice. If x is a binomial random variable where n equals 20 and p equals 0.88, that probability is that, then a is equal to. Okay, so the probability of x being bigger than or equal to 16, given that x is bigger than or equal to a, means that a definitely has to be less than 16 for this to even be a question worth asking. Okay, and so therefore, does it? Yes, it does. And so then the probability of this conditional probability is the intersection of those two things. So that would be probability x is bigger than or equal to 16 over the probability that x is bigger than or equal to a has to be 0.9175. I think I can probably get my calcs to just solve this. So let's set this up. Let's solve an equation. It's going to be a bit ugly to set up. I'm going to need probability of x being bigger than or equal to 16. So that is menu 5, it's binomial, b. So number of trials is 20, probability of success is 0.88, lower bound for the numerator is 16, and upper bound is going to be 20. Let's see how the CAS goes with this. And then the denominator is going to be, the denominator is going to be that exact same thing except for, and it won't like it. Let's see what it does though. 55b, number of trials is 20, probability of success is 0.88, lower bound is our unknown value, upper bound is 20. Yep, we know. And we know this has to equal 9175. We'll see if we can solve this. We want to solve for A. A is 11. Okay, now this is interesting, and this is worth being cautious about because I've just looked up the answers, and the answer is B, and it's actually 12. And actually, if I have a look at checking this, so if I do menu 55B, and I get my N is 20 and P is 0.88, and my lower bound is 16 and my upper bound is 20. Okay, so we get that value there. And then if I look at if A is 11, so for this conditional probability, I would be doing this value divided by this value. I actually get 0.9173, not 0.9175. Whereas when I do this, so there must be a sort of rounding problem happening here, and I do this probability with 16 over 12, I get 0.9175. So actually, rather than solve the equation, I might be better to just work my way through the options, just changing that n value. You know, you could literally just work your way through, make it this value 11, gives you that, change it so that this value is 12. Oops, sorry. 12, which gives you what you want. You can see if this value is 13. Oops. It's too much. So 12 is definitely the answer here. It's interesting that solving the equation, though, didn't actually give me the right answer. So just be a bit cautious about that, solving those equations with binom PDF and binom CDF in them. I suspect it was sort of a rounding thing. It's not this value here. This answer here isn't exactly A. Isn't exactly 11. And so therefore it's actually just slightly over 11, and so therefore we're going to need 12. But I wouldn't be making that assumption. I actually think you're better to test the options rather than solve the equation, or at least work out the equation so that if we rearrange this, this is the probability that x is less than or equal to A. So if multiply is going to be probability x is less than or equal to 16 divided by 0.9175. Let's see if this gives us the right answer. So probability x is bigger than or equal to 16 is that, and if I divide that point by 0.9175, I get that. So that is what my binomial probability needs to equal. So if I now see if I can solve that, oh sorry, didn't need simultaneous, menu 3.1, solve menu 5.5b, 20 trials, 0.88, lower bound is unknown, upper bound is 20. Okay, and we need that to equal this number. We solve that for A. That also only gives us 11. Yeah, so I'd just be a bit cautious about that. I would just, given that it's a rounded value, and you can tell that it's rounded by that decimal place after it, there wouldn't be a dot after it if it was exact. I would just make sure you then check, just go back and check. So actually, it is A equals 12. And in fact, therefore, given that, probably just working your way through these options, as I said, editing this calculation here, this one here, and changing this value down here, from 11 to 12 to 13, etc., until you get the one that gives you the answer you want, is probably the safest option here. So B is the answer to question 18. Question 19. A box is formed from a rectangular sheet of cardboard which has a width of A units and a length of B units by first cutting out squares of side length X units from each corner and then folding upwards to form a container with an open top. The maximum volume of the box occurs when X is equal to. Okay, so this is a really standard Year 11 polynomial application question. You've got a sheet of cardboard, a rectangular sheet of cardboard. It's just more variables in this one. In this case, it's going to have dimensions that are A and B. We're going to cut out corners of length X. Okay. So when we do that, we'll be able to fold up an open sort of box where this length is A minus 2x and this length is B minus 2x and this vertical height is X. And so therefore the volume of the box is going to be X times A minus 2x times B minus 2x. And to find the maximum volume of the box, we're going to need dv dx. Okay, I'm going to define my volume function. It is going to be x times, again you'll need those explicit multiplications, a minus 2x times b minus 2x. I'm going to differentiate it. And we get this 12x squared plus negative 4a minus 4b x plus ab equals 0. We're going to solve that. Okay, and we get two solutions. So let's just have a look at both of them. Yep, so it's got positive a and a plus b at the end there, and the other one also has a plus b at the end there. It's just because of its unhelpful factoring out of the negative from the whole thing. So we're actually going to have a plus b plus and minus the square root of that thing, a squared minus ab plus b squared, all over 6. Okay, so then given I've got minus 2x and minus 2x, this is a positive cubic, so the shape of this cubic goes like this. So we've got two turning points. The first turning point is the maximum and the second turning point is the minimum. And so therefore the first turning point is going to be the one with the minus in it. So we actually are going to have maximum when x equals a plus b minus the square root over 6. Alright, so a plus b minus, so I think that's option D. Okay, and then the last multiple choice, question 20. A soccer player kicks a ball with an angle of elevation of theta degrees, where theta is normally distributed around a variable with a mean of 42 and a standard deviation of 8. The horizontal distance that the ball travels before landing is given by the function d equals 50 sine of 2 pi. The probability that the ball travels more than 40 meters horizontally before landing is closest to. Okay, so I think we need to work out that if the horizontal distance is 40, what does that mean for the angle? Okay, so 50 sine of 2 theta is essentially so this would be pi and this would be pi on 2. This angle is theta. Okay, but we're obviously in degrees. We want all our answers in degrees. So this is clearly 90 degrees and this is 180 degrees. So obviously there's an implied domain restriction here because you can't, if you're kicking a ball with an angle of elevation of, if you're kicking a ball and the ball's going to go, then this angle of elevation is not going to be more than 90 degrees. You're not kicking the ball backwards this way, okay? So the domain restriction is obviously that it's somewhere between 0 and 90. This is our distance. The maximum distance is 50. You can see that. So we want to know the probability that the ball travels more than 40 meters. Okay, so therefore we want to know when the distance is 40, what range of angles give a distance that is bigger than 40. Okay, so we're going to need those two values. So the first thing we need to do is solve 50 sine of 2 theta equal to 40. Just between 0 and 90. I'm going to put my CAS in degrees. Oops, sorry. So menu 3.1. Oops, sorry, I'm in the wrong row. Menu 3.1. We're going to solve 50 sine of 2x equal to 40 for x, and we're going to do that for x between, so given that 0 is less than x, which is less than 90. Control enter. Okay, so theta is 26.6 degrees and 63.4 degrees. Okay. Alright, so then theta is a normally distributed variable with a mean of 42 and a standard deviation of 8. And we want therefore to know the probability that theta is between 26.6 and 63.4, because those are the angles that give me a distance of more than 40 meters. Okay. Alright, so let me maybe write these numbers down a bit more accurately than that, because I can't copy and paste two numbers at once into my normal distribution. So let's make that 26.56505118 and 63.43494882. Given it's multiple choice, I probably could have used the random ones and just gone with whatever was closest. But let's have a look. Alright, so menu 5, we've now got normal CDF 2. Our lower bound is 26.56505118, and our upper bound is 63.43494882, and our mean is 42, and our standard deviation is 8. Alright, and that is 0.969469, etc. So option A. Alright, there's the multiple choice. Let's move on to the extended answer. Okay, so section B. All the standard instructions, more than one mark, appropriate working must be shown, exact values unless told otherwise, diagrams not to scale, etc., etc. Okay, the diagram below shows part of the graph of y equals f of x, where f of x is x squared on 12, so it's just a simple parabola with a bit of a dilation. State the equation of the axis of symmetry of the graph of f. Okay, so as I said, it's a very standard parabola with its turning point at the origin. So the axis of symmetry is a vertical line, x equals 0, which is the y-axis. State the derivative of f with respect to x. So f dash of x is going to be 2x on 12, which is just x on 6. The tangent to f at point M has gradient -2. Find the equation of the tangent to f at the point M. Okay, so our CADs can find an equation of a tangent for us, but we actually need to know what this x value is here, where the gradient is -2. So we know that f dash of x equals -2 at this point. So let's solve that. So it's quicker by hand because they're very simple functions. X on 6 is going to be -2. That's the derivative is -2, so x is -12. Okay, so up here on my graph, this must be -12, and so I want the equation of the tangent when x equals -12, and my CAS can do that for me. Equation of tangent. So I've got a bit of a lag with my pen. Hopefully that calms down in a minute. So menu 4 for calculus, 9 for tangent line. We want the tangent line to the function x squared on 12, and we want that when x is equal to -12. Oops, sorry. X is equal to -12. And that equation, it must be y equals something. It's really common for students to just write down -2x minus 12. It's something I talk about in the examiner's report a lot. Sorry, I've still got a really big lag. -2x minus 12 is my equation of the tangent. Okay, part D. Diagram below shows part of the graph of y equals f of x. So it's still the same f of x, x squared on 12. The tangent to f at the point M, so that's the tangent we've just found. So we now know that this equation is y equals -2x, was it minus, sorry I lost track, minus 12, yep. I've still got it sitting in my CAS there. Diagram below shows part of the graph of y equals f of x, the tangent to f at the point M, and the line perpendicular to the tangent at the point M. Okay, so this is the normal. So let's also find the normal at M with our CAS. Menu 4 for, oh, sorry. Menu 4A for normal line, and it's also to x squared on 12, comma, when x equals -12. Alright, so that equation is y equals x on 2 plus 18. Alright, that's the answer to D part 1. Find the equation of the line perpendicular to the tangent passing through point M. So that is the normal at x equals negative 12, and that is y equals x on 2 plus 18. Okay, the line perpendicular to the tangent at point M also cuts f at point N, as shown in the diagram. Find the area enclosed by this line and the curve y equals f of x. Okay, so we need the coordinates of the point N, first of all. So we need to solve f of x equals the normal line, so x on 2 plus 18. Okay, so by that I mean f of x being, I might actually write it out here because I haven't defined it in my CAS, f of x being x squared on 12. So I'm solving x squared on 12 equals this normal line for x. Alright, that happens when x equals negative 12, which we already knew. That's where we found the normal from. And when x equals 18. Okay, so this point here is negative 12, and this point here is 18. Okay, so we want to find the area enclosed by this line and the curve y equals f of x, so that's that shaded area there. So the line is always the top function over that region, and the parabola is the bottom function, so it's just a simple single integral. So the area is going to be from the integral from negative 12 up to 18 of the line, which is x on 2 plus 18, minus f of x, which is x squared on 12. And it doesn't tell us to round, so it must give a nice exact value. So shift plus negative 12 to 18 of that normal line, which I've got there. Oh, sorry, should have just typed it, it was quicker. X on 2 plus 18, and then minus f of x, which is x squared on 12 with respect to x. Okay, so that area is 375. Do we have any distance units here? No, no units. So I'm just going to call that square units. Okay. So mark scheme seems pretty straightforward so far, I think. It's 1 mark for x equals 0, 1 mark for the derivative equals x on 6, 1 mark for working out that the point M has an x coordinate of negative 12, and then 1 mark for your equation of the tangent, making sure you have an equation. This is a 1 marker for the normal. 2 marks here. 1 would be for getting this 18, whether that's just seen there, I think. But I would like to see an equation, to be honest. I'd like to see a method there. I'm not sure how the mark scheme would have been set up. And an answer mark here for that value. Okay, part E. Another parabola is defined by the rule g of x equals x squared on 4a squared. So we're generalizing the x squared on 12, where a is bigger than 0. A tangent to g and the line perpendicular to the tangent at x equals negative b are shown. Okay, so we've got both a tangent and a normal at x equals negative b. Find the value of b in terms of a such that the shaded area is a minimum. Okay, so in order to be able to work out where the shaded area is a minimum, we need an expression for the shaded area first of all, which means we're going to need to work out what this point is here. So we first of all need the equation of the normal at x equals negative b. So the normal, let's try that again. The normal at x equals negative b. So I might define this function. So define g of x, g of x is x squared divided by 4 times a squared. Okay, so there's g of x. We now want the normal, so menu for a to g of x, comma, when x is equal to negative b. Okay, so that is y equals 2a squared on bx, and then plus 8a to the 4 plus b squared on 4a squared. I'm going to call this the normal at x. just so I've got some notation to help me. I don't normally like defining my own functions, but I don't really want to have to write that expression out again. So the area, okay, let's call it the shaded area, and then I'm going to give it a name too. Let's call that a of x. That's going to be the integral, oh no, before we find the area, integral expression for the area, sorry, we need to find the coordinates. Oh, I shouldn't have used n because, oh no, we don't have n. We need to find the coordinates of this point over here. So I'm going to solve my normal. So I need to solve n of x, my normal, equal to my function. And that should give me x equals negative b and something else. So let's do that. And solve my function equal to my normal for x. Ooh. That's horrible, isn't it? Why have I got a cos involved in that? Oh, it's not f, it's g. Sorry, I must have another function defined as f of x, a trig function. Sorry, this is, let's try that again. It's not f of x, it is g of x. So that would be wrong even if you had the thing defined properly. So you need to make sure you use notation consistent with the question. So we're going to solve g of x equal to my normal equation, which is that. I'm going to solve that for x. That's much nicer. X equals b and 8a to the 4 plus b squared on b. Okay, so that must be this value here. Alright, so then my shaded area, I'm going to call it a of x, is going to be the integral from negative b to 8a to the 4 plus b squared over b of my normal, which is n of x, minus my curve, which is g of x. Alright, let's do that. I hope we get something that doesn't look too ugly. So we're going to go from negative b to 8a to the power of 4 plus b squared over b. And we're going to need our normal, which is up here. And Control C that. Control V. Take away g of x dx. Okay, that's that, which is not as horrible as it could have been, but it's also not very fun. 64a to the 12 plus 48 a to the 8b squared plus 12a to the 4 b to the 4. Actually, I've just realised that this shaded area is not a of x, it's a of a and b, so let's just call it a. Sorry, let me finish copying that. So plus b to the power of 6 all over 3a squared b cubed. Okay, so I want the shaded area to be a minimum, so I want to solve that equal to 0. And I want to find the value of b in terms of a, so I want to solve it for b. So I'm going to solve this equal to 0 for b. I just realised I'm not making the area equal to 0. I'm going to need the derivative of that to equal 0. I'm wondering if I can think about that in a less complicated way. So we're making the shaded area minimum. Nope, okay. So I'm going to do dA, d... Now, because we want to find b in terms of a, it's b that we're interested in. B is sort of an x value, whereas a is just kind of a dilation factor. So I think we're going to differentiate this with respect to b and solve that equal to 0. I'm not going to write out the derivative because I think it'll be ugly. So let's solve shift minus the derivative with respect to b, this, which is our shaded area expression. Let's solve that equal to 0 for b. Okay, and we get b equals plus or minus 2a squared. But let's just think about whether it could be both of those. So what do we know about a? So b is a positive value. A is also positive. So if b and a have to be positive, if a is positive, then yeah, b, it can't be the negative. But b is bigger than 0, so b equals 2a squared, because regardless of what, a has to be something positive. Even if it wasn't, when we square it, it's positive. And so the only way for b to also be positive is if it equals positive 2a squared. Okay, so that's a little bit ugly for quite so early on in the paper. I really don't remember doing this paper. I definitely did it last year, but anyway, let's see. Question 2. On a remote island, there are only two species of animals, foxes and rabbits. Oh, I think I remember the foxes and rabbits, though. The foxes are the predators and the rabbits are their prey. The populations of foxes and rabbits increase and decrease in a periodic pattern, with the period of both populations being the same, as shown in the graph below. Where time t is measured in weeks. Okay. 1 point of minimum fox population, 2,700, and 1 point of maximum fox population, 100, 2,500, are also shown on the graph. The graph has been drawn to scale. Okay, so it tells us in the general instructions we can't assume diagrams are drawn to scale, but it's specifying that this one is, and we've actually got a really clear scale drawn. The population of rabbits can be modelled by, so we've been given the function for the population of rabbits. State the initial population of rabbits. So let's define some functions in our CAS. Just get rid of, clear things out. So menu 1, let's define r of t as being, I'm going to go back to radians in a second, I changed it to degrees earlier in the paper. Sine of pi times t over 80 plus 2,500. Let's just change that to radians. Okay, state the initial population of rabbits. So that's going to be r of 0, which should be 2,500. We can see it off the graph. We can work it out from our equation very simply in our heads, and we can confirm it with our CAS. So the initial population of rabbits is 2,500 rabbits. State the minimum and maximum population of rabbits. Okay, so min value of r is going to be 2,500 plus the amplitude, which is 17, sorry, that's maximum, so minus the amplitude, which is 1,700. Which is 800. And maximum value of r, so maximum population of rabbits, is 2,500 plus 1,700. So 4,200. Rabbits and rabbits. Oops, 2 B's. Okay, again, we probably could have read those off the graph. It's drawn to scale, so it shouldn't be really any excuse for getting those wrong. State the number of weeks between maximum populations of rabbits. Okay, so that should just be the period. So we should also be able to read it off the graph there. It looks like 160, if I read it accurately. But we should also be able to tell that from the period. Okay. So the period, it's a sine function, so it's going to be 2 pi divided by pi on 80, which means it's 2 pi times 80 on pi, so 1,600, sorry, 160, as I said, weeks. So nice and easy so far. All of that could have been read off the graph, but also I think important to have an understanding of what's happening with those trig functions. Show that the population of foxes can be modelled by the rule this. Sorry, the population of foxes can be modelled by this rule. Show that A equals 900 and B equals pi on 80. Now, I didn't like this question last year. I remember this as well because I think to show that B equals pi on 80 is really trivial because you are told that the periods are the same and therefore this dilation factor should be the same to make the periods are the same. So there's not really anything to show, but you should probably draw that information together to make that statement. Okay, so R and F have same period, which implies same dilation factor from the y-axis, which means that B is going to be pi on 180. Sorry, pi on 80, which was the same as it was in R of t. I'm going to write R of t here as well. Sorry, let me just get it. 1700 sine. So that's the dilation factor from the y-axis. Show that A equals 900, so that will be the amplitude. So we know that the range of F is going to be 1600 plus A, minus A, and 1600 plus A. Which implies that 1600 minus A has to equal, we got our minimum, we're told the minimum value was 700. And 1600 plus A is maximum value, we've got that point on the graph, 2500. And so both of these things mean that A equals 900. I think both are slightly trivial show that's, but particularly the B. I suspect they wanted you to use the 100 and the 20 from these 2 points and say that 100 minus 20 is 80, that's half the period's 160 and therefore the period, but you shouldn't need to work back from the period to the B value because you're actually explicitly being told those periods are the same. It said that back here. With the period of both populations being the same. So yeah, this felt like a pretty trivial question. I wasn't quite sure what they were after. Actually, let me just have a quick look at the examiner's report and see if it mentions anything explicitly. Okay, so it did say this was a show that question, appropriate working needed to be shown. It acknowledged that students used a lot of different methods. Some students set up simultaneous equations and solved them using the 2 points. So I really think they probably wanted you to use the 2 points they gave you, but there was just so many other ways to do it. I don't think, as long as you were really clear about where your values came from, then I think, something like what I've got written here has to have been accepted as correct, and I'd be, very disappointed if it wasn't. Find the maximum combined population of foxes and rabbits. Give your answer correct to the nearest whole number. Okay, so the combined population is going to be f of x, ft plus r of t. So let's get a new function. Because it won't just be the two maximums added together, because you can see that they are not at a maximum point at the same time. So we need to think about a new function, c of t, which will be r of t plus f of t. Let me define a new function. Actually, I haven't defined f of t yet, the fox one. Let me do that. F of t is going to be 900 times sine 80 t minus 60 plus 1600. Okay, so then we need another function, c of t, which is going to be our combined population, which is r of t plus f of t. Let me just see what c of t. Okay, so that would be the rule for that. Let's have a quick look at it. Might put them all up here. So let's have our foxes. I need to put x to put it on the axis. I'll put r of x. And then I'm also going to put c of x. And we obviously don't have an appropriate window at all. So let's just have a quick look at this window. So menu 4.1, let's make the x's go from minus 20 to 340. And let's make the y's go from negative 250 to 4,500. Just want that to be auto again. Sorry, obviously. Okay, so there's my graphs. Okay, let's make this y much bigger for our combined population. Oh, too big. Okay, so we can see the combined population is also a nice periodic function, but as I said, you can see the maximum is not happening in line with either of the other maximums. Let's see if we can just see what's happening here. So menu 6 maximum, if it's a nice whole number, so that graph, there's the maximum. Okay, that's just a rounding issue, so change the attributes of that value so you can see more decimal places. Okay, so it's not a nice exact number. So what did the question actually say? Find the maximum combined population of rabbits. Give your answer correct to the nearest whole number. Okay, so nearest whole number, that would be 5339. So the max value of C, 5,339. Okay, then the part D is what is the number of weeks between periods when the combined population of foxes and rabbits is a maximum? Okay, so that's just the period of C, and the period of C will be the lowest common multiple of the periods of R and F, given that it's a sum of two functions. And the periods of R and F are both 160, so the period of C will also be 160. So this will also be 160 weeks, should have the same period. Okay, the population of foxes is better modelled by the transformation of y equals sine of t under Q, given by this. Okay, so obviously this is a matrix question, so this is no longer relevant in 2023. But this is a question about transformations, and the way this would be phrased would just be different. So all this notation is, and you don't need to understand it, but the way this could be written differently would be to say that I don't think this is the notation they would use, but essentially they're saying that Q of Ty is, let me write it, so it's going to be 90 on pi t plus 60 and 900y plus 1600. Okay, so what it's saying is when we do the transformation Q, and usually they use capital T, so this was a change of notation for this as well. When we transform any point on this graph, and every point on this graph has coordinates ty, so it's not xy in this problem, we've got t values, not x values, that gets transformed to be this point. So all the t coordinates get multiplied by 90 on pi, and we add 60 to them, and all of the y coordinates get multiplied by 900, and we add 1600 to them. Now, whether it would be given to you in this form, whether it might be written as something like the point ty is transformed to the point 90 on pi t plus 60, and 900y plus 600, whether those transformations might be given to you in a written format, so whether you might be told that the graph of y equals sine of t is dilated by a factor of 90 on pi from the y-axis and translated to the right by 60, and dilated by a factor of 900 from the x-axis and translated up by 600, or some variation of that, you should then still be able to do this question. However you've been given those transformations. This is just a notation for giving you a sequence of transformations. So I'm going to still answer this question from this point, because I think you could be given a transformed point like this. So the point ty is transformed to the point whatever, and therefore then we should be able to answer this question. So we want to find the average population during the first 300 weeks for the combined population of foxes and rabbits, where the population of foxes is modelled by the transformation of y equals sine of t under the transformation q. Give your answer correct to the nearest whole number. Okay, so there's quite a bit to do here. So we need to work out what this transformed equation is, and then we need to do various other things. So the first thing we need to do is apply these transformations to y equals sine of t. Okay, so what we learned from the transformation thing is that the image of t is 90 on pi t plus 60, and the image of y, the result of having applied the transformations to y, is 900y plus 600. If we want to apply those transformations into an equation, we need t and y to be the subject of these. So this means that t is going to be t dash minus 60 and then times pi on 90. And y is going to be y dash minus 600 over 900. Okay, so y equals, I haven't got enough room here, y equals sine of t is going to become y dash minus 600 over 900 equals sine of pi on 90 t dash minus 60. And so if we make y dash the subject here, we're going to get 900 sine pi on 90 t dash minus 60 plus 600. Okay, so this is our new version of the foxes. Okay, so now f of t is this, 900 sine pi on 90, don't need a dash anymore, t minus 60 plus 600. Okay, so that's my fox population. So now I'm going to call that f2, the second version of the fox population, or fq maybe, after the transformations according to q. Okay, so anyway, so c of t, so c2 of t, so our new combined population is going to be our original rabbit population plus our new fox population. Okay, so then we want the average population during the first 300 weeks. So let's do some work on our CAS to define some things. So I'm going to redefine f of t as, so that's plus 600 now. And this is 90. Otherwise everything else is the same. Okay, so c of t is still the same. So we now need, so let's have a look now that I've redefined that my graphs should have changed. So yeah, you can see those graphs have moved. So f is now a lot lower. F is a bit problematic because there are times when we have negative fox population. Sorry, that's because I copied that wrong. I read it wrong. That's 1600. So this is 1600, 1600, 1600, 1600. So where there's 600, that's a 1600. That's better. Okay, let's fix that again. So f at t, that should still have been 1600. That didn't change. So actually the only thing that's different from this new version of t is that dilation factor is now pi on 90, not pi on 80. So we've got a slightly different period for the foxes. Okay, so now that's our situation. So we want, in this question, find the average population during the first 300 weeks for the combined population of foxes and rabbits. So we want the average population, the first 300 weeks, so average value between 0 to 300. It's going to be this. We need our new combined population. Okay, so nearest whole number. So 1 on 300. Shift plus 0 to 300 of my new C of t, which is still just called C of t in my CAS. I just redefined them. We want nearest whole number, so let's hit Control Enter on that. So that's approximately 4,142 animals. Foxes and rabbits is the average combined population of those first 300 weeks. Okay, so then over a longer period of time, it's found that the increase and decrease in the population of rabbits gets smaller and smaller. The population of rabbits over a longer period of time can be modelled by this rule. Okay, so let's define that in our CAS. Menu 1 S of t 1700 times e to the power of negative point. Now everything after this asks for rounded values, I think, so I'm okay to define this as 0.003, but if I need an exact value later, I might need to come back and redefine that as being 3 on 1,000, so I can get exact answers. So let's see how we go. Okay, times sine of pi on 80 t plus 2,500. Sorry, 2,500. Okay, find the average rate of change between the first 2 times when the population of rabbits is at a maximum. Okay, the first 2 times when the population of rabbits is at a maximum. So let's go back to what we learned about rabbit population. Okay, so rabbit population. Alright, so we know that the period for rabbits is 1,600. Okay, so that's the end of the period there. Sorry, I didn't mean to change pen colour. So 1,600 is the average. We'll be back at that average value at, sorry, 160 is the, sorry, let's go again. 160 is the end of the period. 80 will be halfway along the period, which will still be at that average value. The maximum will be halfway, so the maximum is at 40, and then the period is 160, so the next maximum must be at 200. So the maximum, the rabbit population is at a maximum when t equals 40 and when t equals 200. So find the average rate of change between the first 2 times when the population of rabbits is at a maximum. Okay, so that is when t equals 40 and 200. Okay, so we want average rate of change. Oh, sorry, my apologies, I've lost my train of thought. I read this S of t as being about the combined population. S of t is the new rabbit population. Okay, so we need the first 2 times when this new rabbit population is at a maximum. So we're going to need to look at our derivative. Maybe let's just have a quick look at what it looks like, because it might actually be reasonably straightforward. S of x. Okay, so it looks like it still has the same period. Let's see if we can, if they're nice exact numbers or not, and if not, we'll solve maximum, and I want the pink graph. So I want that point there. Okay, so then, no, that's not very nice. So let's find them algebraically. But at least graphically we can see that the first positive, the first place where the derivative is 0 will be a maximum, and then the third place where the derivative is 0. Okay, so let's have another look. Let's solve the derivative of S of t equal to 0 for t, and it's periodic. Let's just do that over that domain that we can see on the graph. That looks like about 0 to 320. Okay, so as I just said, we saw from the graph that it'll be the first and the third one here that are the maximums. Okay, so s dash t equals 0 gives us t equals 38.1, 118.1, 198.1, and 278.1. Okay, and these are the maximums. Okay, so then we need the average rate of change. Okay, so that is going to be S at 198.1 minus S at 38.1 over 198.1 minus 38.1, which should be 160 because that's the period. The distance between maximums is the period. Okay, so let's get these a bit more exact. So let's work out S of 38.05840453, and let me just scroll this one across so I can see it while I type here. S of 198.05840445. It's the same decimal. Okay, so the average rate of change is going to be that value minus that value over 160. And we want this to one decimal place, so it is negative 3.6 rabbits per week. So the average rate of change is decreasing by 3.6 rabbits per week over that period. And we can see that with the graph. We can see this pink graph is the one we're interested in. It's clearly going down, so it should definitely be a negative average rate of change. Find the time where t is bigger than 40 in weeks when the rate of change of the rabbit population is at its greatest positive value. Give your answer correct to the nearest whole number. Okay, so what we need to observe from this graph here, let me just get rid of the graphs we don't need so we can see a bit more clearly. We want F4, I don't want F3, I don't want F2, and I don't want F1. Oops. Okay, I've still got that point sitting up there, but we'll ignore that for now. Okay, so what we can see is the effect of this exponential part of the function, let me just make that bigger, means that the amplitude is getting smaller and smaller and smaller as we go. And so what we can actually see is with between every max and min, the gradient is getting less and less steep. So we want the rate of change of the rabbit population, so the gradient of this pink graph, to be at its greatest positive value. And we want that to be where t is bigger than 40. So t is 40 is going to be just past this. Let me just grab this so that I can actually draw on it over here so you can see what I'm talking about. Sorry. Apologies for that. I just had to move a window around that you can't see. Okay, so if I just bring this over here for a minute, I might delete it in a minute, but just so I can draw on it. So this is the graph that I'm looking at on the CAS. So I've already got that point 38. So t is 40 is past here. Okay, so we want the rate of change of the rabbit population is at its greatest positive value. Okay, so it's more steep here than it is here, and it's even less steep. So it's getting less and less steep between turning points. So therefore, it's going to it's going to be the maximum gradient in that interval there that we're interested in, so between those two turning points. Now we've calculated all these turning points, so it's going to be between 118.1 and 198.1. We just calculated from the previous one that this is, oh no, this is 118.1, this is 198.1. Okay, so we know it's going to be the maximum gradient in that interval there. That will give us the maximum positive gradient. So we want to find the time in weeks, so we want to know this t value, okay, when that maximum gradient happens. Alright, so let's go about calculating that. Okay, so I'm going to need the derivative of the derivative, which, while second derivative isn't part of the methods course, they seem to be very fond of asking you about it at the moment. So we want to know where that is at its maximum, but we want that to be over that interval from 118.1 to 198.1. And I know those are rounded values, but it's not going to be near either of them, so we could just give those rounded values. So let's do that over here. Let's solve the derivative of the derivative. Now there is a second derivative function in your CAS, but as I said, second derivative isn't part of the methods course, so you may not know how to do that. Again, that's why it frustrates me a bit that I ask you these things. Okay, so solving the second derivative equal to 0 for t, but we only want, given that we are between 118.1 and 198.1. Alright, so that happens when t is about 156.1. Find the time where t is bigger than 40 in weeks. Give your answer correct to the nearest whole number. So therefore, it's 156 weeks. Over time, the rabbit population approaches a particular value. Okay, so yes, we can see, if we have a look at our graph here, let's make this even bigger. We could see that the oscillations are getting smaller and smaller and smaller, and so hence we're approaching a particular value. State this value. Now this should just be this plus 2,500. On my graph here, on my graph here I could just add y equals 2,500 to see. So yeah, the graph is oscillating either side of that 2,500, so that is going to be the population that we're approaching. Sorry, just pause the video for a moment there. It's a bit of a lag and I couldn't actually see the question. Okay, question 3. I'm quite glad to be done with the foxes and rabbits. Mika is flipping a coin. The unbiased coin has a probability of 1/2 of landing on heads and 1/2 of landing on tails. Let x be the binomial random variable representing the number of times that the coin lands on heads. Mika flips the coin 5 times. Okay, so let's get rid of all of that. So we have x is defined for us. X is a binomial variable. N is 5. She flips the coin 5 times, and the probability of getting a head, which is what x represents, the number of heads, is 1/2. Find the probability that x equals 5. So that's we want, it doesn't tell us about rounding, so it's going to be nice and exact. And that's because the probability is 1/2. So menu 5, it's a binomial PDF because it's a single value. N is 5, probability of success is 0.5, and we want x equals 5. That is going to be 0.03125. That should be nice and exact. If I bring that down here, there's no more decimal places than that. And that's because it is just 1/2 to the power of 5. So let's just check that. Oops, the power of 5. It's 1 on 32, which is that value there. Okay, so either of those. Find the probability that x is bigger than or equal to 2. Menu 5, B. Number of trials is 5. Probability of success is 0.5. we want to go from 2 to 5. Again, let's check. Yes, that's a nice exact value again. So probability that x is bigger than or equal to 2 is 0.8125. Find the probability that x is bigger than or equal to 2 given that x is less than 5. Correct to 3 decimal places. Okay, so it's a conditional probability. We need the intersection of these two things. So probability of x being bigger than or equal to 2 given that x is less than 5. The intersection of those two things is x being between 2 and 5, inclusive of 2 and not inclusive of 5, over probability that x is less than 5. Now we need to remember with our binomial that that is less than 5 is the same as less than or equal to 4, because it's a discrete variable, and it'll be 4 that we need to put into the CAS. And we want this answer to 3 decimal places. Okay, so menu 55B. We have 5 trials. Probability of success is 0.5. Our lower bound is 2 and our upper bound is 4. And then I'm just going to copy and paste that. This time the lower bound is 0. Okay, so it is that probability divided by that probability. And that answer, correct to 3 decimal places, is 0.806. Find the expected value and the standard deviation for x. Okay, so the expected value of x, expected value for a binomial variable is just n times p. So that's going to be 5 times 0.5. So that would be 2.5. And the standard deviation is n times square root of, sorry, it's the standard deviation. Square root of the variance. So that is the square root of n times p times 1 minus p. So the square root of 5 times 0.5 times 0.5. And that's for rounded, it must be exact. Square root of 5 times 0.5 times 0.5. That's not very nice, so let me write that better. Let's write that as half times half. So that's the square root of 5 quarters, which is root 5 on 2 as an exact value. Okay, so the height reached by each of Mika's coin flips is given by a continuous random variable h with the probability density function this, where h is the vertical height reached by the coin flip in meters between the coin and the floor. State the value of the definite integral that. Okay, let's define our function. It's going to be a bit ugly with being f of h, but that's okay. They're really testing your ability to be a bit flexible about the variables here. A times h squared plus b times h plus c. Oh, c I've got defined as something. It's clear A to Z, I don't need any of them. Okay, menu 1, let's try again. F of h. Try again. F of h equals a times h squared plus b times h plus c. So C is no longer bold, so it's no longer defined as something. I would never define a function with a domain restriction. There's no need to define this as a piecewise function because it's 0 elsewhere, so it's really just got one part to it. So I would just define the function, and then I would interpret my answers in the context of the domain throughout. So state the value of the definite integral. Okay, so we want shift plus. I don't think it's going to be a value. I think it's going to be in terms of A and B and or C. 1.5 to 3 of f of h with respect to h. Okay, so, and again, if we wanted to not have decimals, rather than put 1.5 in here, rather than put 1.5 here, if I'd put 3 on 2, it would have given us all of that very nicely. So again, state the value. I don't love that. Or actually, can we work out what A and B and C are? No, we know the total area is 1, but we don't have enough information to work out A, B, and C. And I've just checked the examiner's report, and indeed the answer is an expression involving A and B and C. So I actually don't like that wording. Okay, so this is, we could either write it as 63 on 8A plus 27 on 8B plus 3 on 2C, or 7.875A plus 3.375B plus 1.5C, either of those. Given that the probability of H being less than or equal to 2 is 0.35, H being bigger than or equal to 2.5 is 0.25, find the values of A, B, and C. Okay, so we've got 3 bits of information here that we can use. We know that that total integral, which we've just found in part A, has to be equal to 1. So we know that the integral from 3 on 2 to 3 of f of h dh has to be 1. We also now know that the integral from less than or equal to 2, so from 3 on 2 to 2 of f at h with respect to h has to be 0.35, so that's 35 on 100, which is 7 on 20. And we know that the integral from 2.5, so 5 on 2 up to 3 of f at h has to be 0.25, so that's a quarter. Alright, so we should be able to solve those 3 equations for A, B, and C. Menu 371. I'm going to have 3 equations, and they'll have A, B, and C in them. And I just need to set up those 3 integrals. So I'm going to use nice exact values in my integrals to ensure that I get exact answers, because it doesn't tell me to round. Three on 2 to 2. Just going to put 35 on 100. It is definitely 7 on 20, but... And then 5 on 2 up to... Oh, sorry, I missed a 3 in there. Yep, so 5 on 2 up to 3. Sorry, I was just checking I had those earlier two entered correctly. So f of h equals dh, and that has to equal 0.25, which is definitely a quarter. Alright, so putting everything in exactly, it should give us A and B and C exactly. So A is going to be -4/5, B is 17 on 5, and C is -167 on 60. If we press Control Enter there, that would be fine to give your answers as A equals -0.8 and B equals 3.4. They're exact, but the C value you would need to write as -2.783 recurring to give nice exact answers. Okay, the ceiling of Micah's room is 3 meters above the floor. The minimum distance between the coin and the ceiling is a continuous random variable d with probability density function g. Okay, so it's going to be g of d, yep. The function g is a transformation of the function f given by this, where d is the minimum distance between the coin and the ceiling, and r and s are real constants. Okay, so again, minimum distance, a bit like that multiple choice question. It's not about minimizing anything, it just means it's the direct, perpendicular, straight up distance, not, you know, the distance between a point and the ceiling. You could go in any direction to get to the ceiling, but it's the straight up, therefore the minimum distance. Okay, so let's think about what we've got here. So our original variable h was the height reached by each of Micah's coin flips And so it was the height from the floor. So that's the distance, h is the distance between the floor and the coin. And then d is going to be the distance between the coin and the ceiling. Okay, so what we have is we have our room, we have the floor, we have the ceiling. We know that the ceiling is 3 meters above the floor, so we know that that's 3. We've got our coin, and we know that this distance here from the floor to the coin is h, and this distance here is d. Okay, so that means that we know that the relationship between d and h is that d plus h has to be 3, and so h equals 3 minus d, or d equals 3 minus h, etc., etc. Okay, so that means that instead of it being f of h, well, h is the same as 3 minus d, so that's the same as f of 3 minus d. And that's actually now, so now that it's in terms of d, it's now g of it. It's now g of d. So this is g of d. So what we've found is that g of d is f of negative d plus 3, which therefore, if we have a look at this, means that r equals negative 1 and s is equal to 3. Okay, so the next part, Micah's sister Bella also has a coin. On each flip, Bella's coin has a probability of p of landing on heads and 1 minus p of landing on tails, where p is a constant value between 0 and 1. Bella flips her coin 25 times in order to estimate p. Let p hat be the random variable representing the proportion of times that Bella's coin lands on heads in her sample. Is the random variable p hat discrete or continuous? Okay, so p hat is technically it's a bit, so x is, if we think about x as being the number of heads, x is definitely a discrete variable. She can either get 0 heads, 1 head, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to 25. Okay, it can take one of 26 different discrete values. Now p hat isn't those values. P hat is the proportion of, but p hat can also only take one of 26 different discrete values. It can only be 0 or 1 in 25 or 2 in 25 or 3 in 25 or 4 in 25, etc., etc. So even though those values are decimal or fractional values, there are still a countable discrete finite number of them, and so therefore p hat is still a discrete variable. Okay, so let's see what we say. P hat can only take one of 26 different values. All the way up to 24 on 25 and 1. Okay. Hence, p hat is a discrete variable. So it is possible for us to count all of the possible outcomes of p hat. There are 26 of them, and therefore it must be discrete. If the possible values of p hat could be anything, then it wouldn't be discrete. This would become, there'd be a tipping point where if Bella flipped this coin, 10 billion times, then we might be starting to get to a point where we might be able to model p hat as a continuous variable, even though technically it's still, there's still 10 billion and one only possible values for p hat. But definitely where she's flipping the coin only 25 times, there are only 26 different possibilities for p hat, and so p hat is still a discrete variable. It's worth noting though that p hat is not a binomially distributed variable. X is the binomially distributed variable, but p hat is still discrete. It's connected to those discrete values for x. Okay, so if p hat is 0.4, find an approximate 95% confidence interval for p, correct to 3 decimal places. Okay, so p hat, the CAS, when we find a confidence interval, we actually need to know the number of successes. We need the x value. So we know that p hat is x on 25, which means that x is p hat times 25. So 0.4 times 25 is 10. So we had 10 successes. So menu 665 for our confidence intervals. We had 10 successes out of our sample of 25. We want a 95% confidence interval, so we're not going to change the confidence level. And the confidence interval correct to 3 decimal places is, let's write this. So we're going to have a 95% confidence interval is going to be 3 decimal places, 0.208 to 0.592 would be our confidence interval. Okay, Bella knows that she can decrease the width of a 95% confidence interval by using a larger sample of coin flips. Correct. If p hat is still 0.4, how many coin flips would be required to halve the width of the confidence interval found in part C2? Okay, so the original margin of error is also on our CAS here. It is 0.1920. Okay, so we want our new margin of error to be half of that. 1920 divided by 2. 0.1920364672. So I'm just copying it out from there. So it's as exact as I can get it. Okay, so I want my new margin of error to be 0.0960. Okay, so the margin of error is 1.96 times the square root of p hat times 1 minus p hat over n, and I want that to be this. Now I'm going to get that 1.96 nice and exactly, so menu 55, inverse normal, 0.975. Okay, there's the 1.96 exactly. So now I am solving that times the square root of 0.4 times 0.6 over n, and it needs to be equal to this margin of error. Oh, sorry, the equals out of the square root, equal to this. And we want to solve that for n. Okay, and so that gave me n equals 99.999. Okay, so n is 100. So she'd need to do 100 coin flips rather than 25 coin flips in order to halve the margin of error. Okay, sorry, I just had a bit of a lag there when I scrolled through the document. Okay, so question 4. Consider the function f, where this is f here, so we've got a function. Let's just clear things here. Let's define our new function. Not going to worry about the domain in the function definition. So it is log e of x plus a half minus log e of half minus x. Half minus x. Okay, part of the graph is shown. State the range of f. Okay, well, just looking at the graph, it looks like the range is going to be r. Okay, if we let's just get things tidied up here again. Oops. Certainly appears as if it goes on and on and on forever. Just asymptoting to those lines. So our range of f is going to be r. Find f dash at 0, so we want the gradient at 0. So let's do that. So let's do f dash of x Alright, so f dash, it's a 2-mark question, so I'm going to write out the derivative here rather than just give a value. It's really important that you're reading the mark allocation. If it was a 1-mark question, I could just straight away get my CAS to do the derivative at 0 and write down an answer. But the 2 marks, I'm going to write out the derivative. Alright, so then f dash at 0, obviously if x was 0 here, we'd have 2 on 1, so it's going to be 2. If x was 0 here, we'd have 2 on -1, which would be -2. We have 2 minus minus 2, so it should be 4. Let's check that with our CAS. Given that x equals 0. Oops. Yep. Okay, so state the maximal domain over which f is strictly increasing. Okay, so f seems to be strictly increasing over its entire domain. It's constantly got positive gradient, never goes down again, and so therefore that would be over the domain -half to half, not inclusive of -half and half because they're asymptotes. Okay, show that f of x plus f of -x is equal to 0. Okay, it doesn't seem to be an awful lot of space for a show that. Okay, so f of x, I've got it defined here on my CAS. So f of x is log e of x plus a half minus log e of half minus x. And then we're going to add that together with f of -x, which would be log e of -x plus a half plus, sorry, it's minus log e of half minus minus x, so half plus x. Okay, so what we have here is to show that, so I'm going to be a bit explicit here, even though I can probably see what's happening. So that's log e of x plus a half, take away log e of half minus x. This is plus log e of half minus x, and this is minus log e of x plus a half. So what we see here is we've got log e of x plus a half, take away log e of x plus a half, and we've got negative log e of half minus x plus log e of half minus x. And so those things are all going to simplify down to 0. Try not to just cross things out. You want to be able to see, so you can see I've quite deliberately used sort of different colours to indicate what's cancelling with what, and just a single line so I can still read everything and see what's happened. But I think it's just quite a big leap just to all of a sudden write that equals 0. I sort of want to see that you can see which bits are cancelling with which bits. Find the domain and the rule of the inverse of f. Okay, so first of all, our original function, let's just write that down again here. So f of x is log e of x plus a half minus log e of half minus x. Now we're either going to do this now or later, but I think in order to find the inverse, I'll do it when I find the inverse. So we're going to let f of y equal x for the inverse. So we're going to have log e of y plus a half minus log e of half minus y, and that's going to equal x. Now, to rearrange this and get those y's out of the logs, I'm going to need a single log. So I'm going to use my log laws. So when I subtract logs, it's because I'm dividing. And so that's going to equal x. And so now we get that y plus a half over half minus y equals e to the x. Okay, so now we're getting there. I've just realised we're in the tech active and we could probably get our CAS to solve this for us. Let's just see what it gives us, because it can sometimes be a bit funny. Let's see what it does if we solve f of y equals x for y. Yeah, no, we're definitely not going to do that. We're getting into hyperbolic trig functions, which those of you who do specialist will understand, but those of you who won't, that's just going to be confusing. Okay, good. So we need to persist by hand. So I'm not loving these halves, and if we could do a number of different things, but I'm just going to multiply the top and the bottom of this fraction by 2, just so it becomes 2y plus 1 over 1 minus 2y. So we haven't actually changed the value. All we did was times top and bottom by 2, so it's still the same fraction. Okay, now we need to get the y's together. So we're going to have to do a little bit of work here. I'm going to multiply to get rid of the fraction. Now I need to be able to get the y's on the same side of the equation. So I need to expand out this bracket on the right, sorry. So it's going to be e to the x minus 2e to the xy. Then I want to get the y terms on the same side of the equation. So I'm going to have 2y plus 2e to the xy equals e to the x take away 1. So I've added that 2e to the xy to both sides, and I've subtracted 1 from both sides. Now I can factor out y. Alright, and now we can divide by that. So we've got e to the x minus 1 over, I might write that as 2e to the x plus 2. Or you might choose to write it as e to the x minus 1 over 2 times e to the x plus 1. Or whatever. Okay, so now we need to answer our question. Inverse of f is whichever one of these you prefer. E to the x minus 1 over 2 times e to the x plus 1. Okay, and we also need the domain of the inverse, which is the range of the original. Okay, so the domain of inverse is the, sorry, struggling with my handwriting, range of the original, which I'm pretty sure we already stated back here when we looked at the graph. The range of f was R. It's interesting, I was just reading the examiner's report here, and they did say that obviously this half than of x on 2 is correct, and if you'd given that as the inverse function, that would be correct. Which frustrates me a little bit because they're giving you questions which produce answers that you have no idea what they mean, but if you copy them down blindly, then that's going to be correct. A number of students, the examiner's report noted they didn't understand that that wasn't tan, it's actually something different, so they wrote tan. Interestingly, the examiner's report also commented on a number of students tried to do this by hand, and that would have been time consuming. But the reality is that when you did it by the CADs, it gave you something that's off the study design, and so it sort of forced you to have to do it by hand. So I'm interested in their comments there. I think they're, kind of unhelpful. I kind of feel like this 2022 paper is set by someone quite different. There's quite a lot about it that I don't actually love. Anyway, fingers crossed for 2023. Part E. Let's let h be this particular function. I'm not going to read all that out. So we've now got a sort of 1 on k involved there, and we've got a different domain happening as well. Oh, no, we don't. That's the same domain, isn't it? So we've just got 1 on k, so that's just a dilation by a factor of 1 on k from the x-axis. So everything's just being squashed down closer to the x-axis. The inverse function of h is defined by this, so we can see that that's a dilation by a factor of 1 on k from the y-axis, which would be what would happen to the inverse function if you dilated the original by 1 on k from the x-axis. The area of the regions bounded by the functions h and inverse of h can be expressed as a function a of k. The graph below shows the relevant shaded area. You are not required to find or define a of k. Okay. Determine the range of values of k such that a of k is bigger than 0. Okay, so we need that area to be positive. So I suspect what's going to happen if we think about understanding these dilations. So as I said, this is a dilation by 1 on k from the x-axis, and this here is a dilation by 1 on k from the y-axis. So what's happening as we make k bigger is that this is getting closer here, so the original function is getting closer to the x-axis, and the inverse function is getting closer to the y-axis. And it should also have asymptotes at y equals negative a half and x equals positive, y equals positive half. So the area is getting bigger as k gets larger because the original function is squashing down closer to the x-axis, the inverse function is squashing in closer to the y-axis, and so that area is going to be getting closer and closer and closer to this value here, and this is a square that is half by half, so that's a quarter, and then obviously there'll be another quarter down here. So the total area, as you make k bigger and bigger and bigger, the area is going to get closer and closer and closer to a quarter plus a quarter, which is half. I suspect that might be a question later on. Perhaps not. But we need to think about, so obviously as k gets bigger, that's okay, but we need to think about what might happen if k were to get smaller. So if we were to, let's say, be dilating by a factor of, if k was half, then we're dilating by a factor of 2 from the x-axis. And so the original function moves further away from the x-axis, and the inverse function moves further away from the y-axis. So it's going to do more like this. And we're going to find that area amount gets smaller. And so therefore there'll be a point where that area amount is going to, this one will move away such that this happens, and this one will move away such that this happens, and then there's actually no area between them. And so you're going to get weird things happening with your a of k function depending on how that's been defined. So, okay, sorry, I just paused the video there for a minute just to have a play around with how best to illustrate this to you. I'm sort of intrigued by this only being a 1-mark question. I think this is sort of quite complex. I understand the idea of it, but how best to come up with the value and to illustrate that to you, I think is difficult. So I've actually defined, I know it says we don't have to find a of k or define a of k. I'm not going to define a of k, but I have defined the new version of f of x and inverse f of x. Oh, actually, sorry, should have been h of x and inverse h of x. But anyway, so I've defined the versions with the k involved. And I just want to sort of try and illustrate this over on the graph. So I'm just going to hope, I just had to redefine this because it did something strange, but if I sketch the graph of f of x, it's going to ask me about a slider for k, and sliders are really problematic because they get a bit stuck and it's hard to get rid of them, and that's exactly what just happened to me, and I had to redo all this, but I'm going to hit OK because I want to be able to show you what's happening here. And then I'm also going to sketch fi. I've defined it as fi of x for f inverse. You can't use if because if has other meanings. So you need to use fi, or you could use something different, but I like to sort of try and give myself indicators as to what it is that I'm actually calculating. So it also has k, and it'll access the same k from the slider. So at the moment k is 1. Okay, so what we actually see here, let me just adjust my window on my slider a little bit. Let me make some, let's move that a little bit. Let's also alter some things here. I'm actually going to make those bigger. Now I could go from -10 to 10. I might also just make the step size, I don't know, that might be too small. Let's go with 0.2. That doesn't matter at all, but that's just personal preference. Okay, so I've changed my slider, I've made it smaller here. It's going to go up and down in values of 0.2 rather than 1, just so I can get a clearer sense of what's happening. I'm also going to adjust the window a little bit. I'm hoping the slider won't get lost when I do this, but let's just see what happens. Yeah, good, came with me. Okay, Let's do it all at once. Okay, so you saw when k is 1, there is no sort of area, whereas when k, here's where we start to get area. Okay, so here's where we're getting a of k is going to be positive when k is 8.4. And so as I said, what you can see is as I make k smaller, there comes a point where, and that's k is 4.2. They look like perhaps they don't, but it's hard to tell. That's k is 4. That looks pretty good. And then, oh, sorry. And then there's no area at all. So it looks like it's happening at about k is 4, where obviously when k is bigger than 4, we get area, but when k is less than 4, is it less than or equal to 4, or what is it? It's around about 4, we don't get area. So one of the interesting things to think about, because you're looking at the function and its inverse, what we're actually interested in is where the gradient of these functions would be 1, because the inverse, remember, this is y equals x, which has a gradient of 1. And so the tipping point of when they won't intersect will be when they both have a gradient of 1 at this point. And so the inverse will start to do that, and the original will start to do that, and they won't intersect at all. So I'm actually going to look at where I want to know what the value of k is when f dash at x is equal to 1 when x equals 0. That's what I want to know, because that's going to be the tipping point. So if I go back over here, I'm going to do menu 3.1. Let me see if I can solve this. I want to do shift minus, no, I'm going to need another bracket first. Do shift, actually let's just do it separately so you can see what I'm doing rather than do it all at once. So if I do the derivative of f of x when x equals 0, it's because it's got a k value currently defined. Can I delete k? Yes. Let's see if we can. Menu 1. This is why the sliders are problematic. Delete variable, and I've got a variable k here. I'm going to delete that. Okay, so now let's see what happens when we do this. Okay, so the derivative at x equals 0, so f dash at 0 is 4 on k. Sorry, it's not f, it's h. Should have defined them as h in my cas. So h dash at 0 is 4 on k. And when that equals 1, that means the gradient of the curve at that point will be exactly the same as the line y equals x. And that's going to be the tipping point where they then won't have an area anymore. Okay, so we can actually see when we solve this that that's going to give k equals 4. Alright, so the area, we can see from our slider experiment that a of k is positive only when k is bigger than 4. There's no area at all between the graphs if k equals 4 and if k is anything less than 4, they don't intersect. Now I've got rid of my slider, you won't be able to see it here anymore. Yeah, because I've got rid of k. It's having a bit of a tantrum, so I can't show you that again. But yes, when k is 4, that's when they're going to have exactly the same gradient as the line y equals x, both the inverse and the original will. And then if k is anything less than 4, they're going to go to a point where they won't actually have any area between them. So explain why the domain of a of k does not include all values of k. Okay, so this is really just about trying to offer some explanation for what we just did to determine that range of values of k. So explain why the domain of a of k does not include all values of k. So obviously we've essentially just worked out in part 1 that the domain of a of k is k bigger than 4. Okay, we had a clarification up here that k has to be bigger than 0, but actually it has to be bigger than 4 for a of k to be defined at all. And so that's just about us offering an explanation. So we're going to say if k is between 0 and 4, so we don't need to think about k outside of those values because the question already specified that k had to be bigger than 0. So if k is between 0 and 4, the graphs are the graphs of h and inverse h are dilated such that there is no bounded area. And as I said, the definition of A of k was the regions bound by the functions. So there is no bounded area between y equals h of x and y equals inverse h of x. Hence, actually it'll be k less than or equal to 4. Hence, k must be bigger than 4 for A of k to be defined. So a diagram might help to illustrate what I'm trying to say. So if k is in this region, then we're essentially going to get graphs. Oh, sorry, that's not the right shape, is it? So we do this kind of thing, and we do this kind of thing. Okay, so I always think sometimes a diagram helps to illustrate what you're trying to say, but some justification as to why k is going to have to be bigger than 4 in order for you to actually get a value for A of k. Okay, and question 5. Consider the composite function g of x, which is f of sine of 2x, where the function f is an unknown but differentiable function for all values of x. Use the following table of values for f and f dash. Okay, so find the value of g of pi on 6. Okay, so g of pi on 6 means that we have f of sine of 2 times pi on 6, which means that we have f of sine of pi on 3. Now we're going to need to know that value ourselves, although we've got our cas actually, haven't we? So we could just type in over here, sine of pi on 3 is root 3 on 2. So that's what we would have got from our special triangle as well. So that's f of root 3 on 2. And then I can go to the table here to find out that f of root 3 on 2 is 3. Sorry. For some reason I can't select the eraser. Let's try that again. There we go. Okay, so the derivative of g with respect to x is given by g dash of x equals 2 cos 2x times f dash of sine 2x. Okay, so that's just chain application of chain rule. So it's going to be, you've got f of something, it's a function inside another function, so you do the derivative of the outside, which would be f dash of that same something, so that's where this bit's coming from, and then you're multiplying by the derivative of the inside, which is this bit. Okay, but they've given that to us. Derivative of g with respect to x is given by this. Show that g dash at pi on 6 is 1 on 9. So we just need to pretty much do the same thing we did above. So g dash at pi on 6 means we're going to have 2 times cos of 2 times pi on 6, that's pi on 3, multiplied by f dash at sine of pi on 3. Okay, so cos of pi on 3 is a half, so that's going to be 2 times a half times f dash at sine of pi on 3, which is root 3 on 2. So we need to go to the table for this one. So f dash at root 3 on 2 is 1/9. Okay, so we've got 1 times 1/9, and so it's just going to be 1/9. Alright, so we've shown that that's true. Find the equation of the tangent to g at x equals pi on 6. Okay, so for the equation of the tangent, now obviously we can't just use tangent line in our CAS because we don't actually have this function, we don't know what f is. So for the equation of the tangent, we need the gradient of g at pi on 6, which we actually just found in part B. So we know that the gradient of the tangent is g dash at pi on 6, which is 1/9. And we need the point, so we need to know what f at pi on 6, or sorry, not f, g at pi on 6 is, which we also just worked out in part A. So we also worked out that g of pi on 6 is 3, which means that the graph goes through the point pi on 6, 3. Okay, so we've got our gradient and our point. So I'm going to use gradient point form, y minus the y coordinate of the point equals the gradient times x minus the x coordinate of the point. And so it's y minus 3 equals 1/9 x minus pi on 54, which is 6/9. And so y is going to be 1/9 x minus pi on 54 plus 3. Okay, so then find the average value of the derivative function. Okay, so not the average value of the function, but the average value of the derivative function between x equals pi on 8 and x equals pi on 6. Okay, so average value of g dash is going to be 1 on pi on 6 minus pi on 8. Oh, sorry, pi on 8. We're going to integrate from pi on 8 to pi on 6, and we're going to integrate g dash because it's that we want to find the average value of. Okay, so let's just simplify this a little bit. 1 on, so I'm going to have, sorry, get out of there. Okay, so let me just do pi on 6 minus pi on 8. Okay, so that's pi on 24, so 1 on that. So that's 24 on pi. Now, the antiderivative of the derivative is g. So that's g of x from pi on 8 to pi on 6. Okay, so this is going to be 24 on pi, g of pi on 6, which we've already worked out, minus g of pi on 8, which we'll need to work out. Okay, so that's going to be 24 on pi, g of pi on 6, we found I think was 3. Let's go back and check. That was in part A. Now let me just also think this through while I'm up here. What would g of pi on 8 be? So that would be f of sine of pi on 4. And sine of pi on 4 is 1 on root 2, or root 2 on 2. So that will be f of root 2 on 2, which, looking at the table, is 5. Okay, so that's going to be 5. Alright, so that's not at all part of the answer to that question, so I might just erase that. That's actually part of the question I'm doing further down. Okay, so we decided that g of pi on 8 is 5. Okay, so we've got 24 on pi times negative 2, and so negative 48 on pi. Okay, so then part E, find 4 solutions to the equation g dash of x equals 0 for the interval 0 to pi. Okay, let me try and think about this. Alright, so g dash of x, what was g dash of x? Okay, so that's it here. 2 cos 2x. Okay, so we need 2 cos 2x times f dash at, I think it's sine 2x. Let's just get it right. Yep. Equals 0. Okay, so that is g dash of x equals 0. Okay, so if we think about null factor law, this means that either cos of 2x equals 0 or f dash sine of 2x equals 0. Alright, let's see what we can get here from 0 to 2 pi. We'll get a couple of solutions out of the cos 2x bit. So cos 2x equals 0, or cos equals 0, cos is the x coordinate, at pi on 2 and at 3 pi on 2. If we want x to be between, yep, so that means 2x is going to be pi on 2 or 3 pi on 2, and so x is going to be pi on 4 or 3 pi on 4. So there are only, 3 pi on 4, sorry. There are only 2 solutions from that part of the function, and we need 4. So we need to focus on how we can get 2 more solutions to this equation, to the second part of this equation, that the derivative of sine, f dash at sine of 2x is equal to 0. Okay, so let's go back up and look at the original function. So we need the derivative of f to be equal to 0. Okay, so we know from the table that the derivative of f is equal to 0 when x, the thing inside the function, is root 2 on 2. Okay, so what we know, so from the table, we know that f dash at root 2 on 2 is equal to 0. And so that means that if f dash of sine of 2x has to equal 0, then sine of 2x has to equal root 2 on 2, which is the same as 1 on root 2. Okay, so exact values, we're talking about pi on 4. Sine is positive, so it's in these two quadrants. Pi on 4 up from here and pi on 4 up from here. So 2x is going to equal pi on 4 and 3 pi on 4. And then dividing those by 2, we're going to get pi on 8 and 3 pi on 8. So there is our 4 solutions. 2 from the cos 2x part of the function and 2 from the f dash at sine of 2x part of the function. I suspect for 3 marks, it's hard to know what the 3 marks would be here. It'd definitely be, you know, 1 for this and 1 for this. Whether there's just 1 for just writing it out equal to 0, or perhaps for identifying that there'll be that according to the null factor law, there'll be 2 separate parts of the equation to solve. It's hard to say, but I think, you know, you would probably still get, I would like to think the marking scheme would be set up that if you just managed to get your way down this part, that you would still get 2 out of the 3. But as I said earlier when talking about the mark allocation, it's very hard to know. And like I said, there's been quite a change in, I feel like this is a very different exam setter setting this paper. The sort of chief examiners and things have changed around a bit over the years, and I think, yeah, I'm not 100% certain how this would be marked, but those would definitely be the answers. So I think overall that was a reasonably tough paper, Exam 2. I thought Exam 1 was reasonably straightforward in 2022, but I think Exam 2 was pretty tough, and it seemed to have quite a different style to it, and I think in areas it verged a little bit off syllabus, which I think makes it a little bit challenging. So it will be interesting to see what 2023 holds with an exam like this, plus the new content as well, which is a little bit tricky. So anyway, I hope that was helpful. It's a fairly long video, I know, but I hope you're able to fast forward back and forth to the questions that you struggled with.